Geographic Information System. Overlay analysis in GIS. Objectives. In this chapter, we will discuss about overlay analysis, vector based analysis, in that point in polygon, polygon in polygon, line in area, raster based analysis, local operations, local neighborhood operations, regional operations, map algebra. Type of overlay approaches: weighted overlay, weighted sum, fuzzy overlay. Overlay analysis. Overlay analysis is an operation in GIS for superimposing the multiple layer of data set that represent different themes together for analyzing or identifying relationship of each layer. Overlay analysis represent the composite map by the combination of different attribute and geometry of data set or entry. Overlay is the operation of comparing variables among multiple coverages. In the overlay analysis, new spatial data sets are created by merging data from two or more input data layers. Overlay analysis is one of the most common and powerful GIS technique. It analyzes the multiple layer with common coordinate system and determine what is on the top layer. Overlay operations combine data from the same entry or different entries and create the new geometrics and new unit of change entry. Overlay operation performs many type of analysis, for example, cropping pattern in the field, dominance of particular ethnic population in a region, age and sex composition of a region, physical landforms of the surface. It is also termed as spatial overlay because it is accomplished by joining and viewing together separate data sets that share all or part of the same area. The result of this combination is a new data set that identify the spatial relationship. Map overlay is used in both model overlay of vector data and overlay of raster data. Overlay analysis often requires the analysis of many different factors. For instance, choosing the site for new housing development means assessing such things as land cost, proximity to existing services, slope and flood frequency. This information exists in different raster with different values of scales, distances, degree and so on. You cannot add a raster to a land cost or a raster distance to utility and obtain a meaningful result. Additionally, the factors in your analysis may not be equally important. It may be that the cost of the land is more important in choosing a site than the distance to the utility lines. How much more important is for you to decide? Even within a single raster, you must prioritize values. Some values in a particular raster may be ideal for your purposes. For example, slopes of 0 to 5 degrees, while others may be good, others bad and still others unacceptable. The following list of general steps to perform overlay analysis. Define the problem. Break the problem into submodels. Determine significant layers. Reclassify or transform the data within the layer. Weight the input layers. Add or combine the layers. Analyze. Vector based overlay. Overlay of vector data combine point, line and polygon feature. In this data model, operations rely on geometry and topology of the surface. Vector based overlay is time consuming, complex and computationally expensive. There are 4 overlay operations in common use. Point in area, also known as point in polygon. Line in area, also known as line in polygon. Area on area, also known as polygon on polygon. Point in polygon. Point in polygon overlay operation will also generate combinative properties of a point attribute of one layer and polygon attribute of analysis layer. It is a spatial operation in which one point coverage is overlaid with polygon coverage to determine which points fall within the polygon boundaries. After overlay operation, points assume the attributes of the polygons within which they fall. It helps in formulating hypotheses about the spatial relationships between the occurrence of the points and the attributes of the polygon. This kind of overlay operation can also be used to calculate number of points located in each of the polygon. Polygon on polygon overlay operation. In the polygon on polygon overlay operations, one should check before starting the input layer it should be topologically correct. If it is correct, output map will also be correct. In the polygon overlay, it is essential to add new intersection and create polygon for new topology. The overlay of two layers of polygon will produce a larger number of polygons and increase the number of interaction zone and arcs. If the new polygon, arcs and set of nodes have been shaped, then meaningful set of layer can be extracted. It is necessary to keep in mind that area should be common to both input features. Point-on-point polygon operations. For example, a farmer wants to know which part of the field has loam soil for the cultivation of crops. The farmer will overlay the map of loam soil polygons on the field polygon to extract a feature that meets both criteria, loam soil and in-field for cultivation of crops. The variables is processed by the farmer. Both are categorically or nominal data type. Mathematicians have developed set of algorithm termed as Boolean operators for handling with this type of data, and GIS analysts exploit in area on area overlay analysis. Line and area overlay operations. Line and area overlay operation need to check linear object or attribute which will combine or merge with area layer. It should be also topologically correct. Suppose one have to know about which road is going in forest or non-forest. Simply one need to overlay the line layer on the polygon, remaining extracted layer will be resulted. The majority of the work in GIS is using vector files, and while the software has some really neat and very complex tool in its toolbars, the basic overlay analysis tools are foundation of all work technicians do. Regardless of how in-depth the project is or how long the technician has been in the field, tools like arrays, intersect and union are so common that two of the three can be found in the geoprocessing short menu, along with some of the foundational proximity analysis tools. ESRI, the makers of ArcGIS, recognize this foundational status of these tools and have created that shortcut menu for arrays of use, which by the way can be customized to include other tools that a technician uses frequently. Arrays. Arrays works like an eraser, removing from features in the input layer all the areas where arrays layer is coincident. That means that the output layer is made up of features consisting of all the areas where the two were not coincident. Arrays is one of our two cookie cutter tools. Intersect. Intersect looks for features which are common to all of the input layers, in contrast to arrays which uses a binary input model or a tool which uses just two input layers. Intersect uses a multiple input model, meaning the tool will find the areas common between two or more input layers. Intersect is used when you want to answer the question, where are the places the input layers have in common? Union versus merge versus append. While arrays and intersect look at how features interact with each other, union, merge and append combine data together from two separate input data sets of same geometry. The difference is union splits up coincident features at the lines where they intersect and adds a field to the attribute table expressing the relationship between the layers. Merge simply combines the features where they exist in the world without any sort of feature altering or attribute table changes or notation, creating a new output data set. Lastly, append, like merge, combines several input data set of the same geometry type. However, the tool append the second, third and fourth etc. criteria layers to the first data set. Raster based overlay. Overlay of raster data sets combine pixel based calculation or map algebra. It is quick, straightforward and efficient data sets for operation. It is known as cell by cell combination or operation. It is computationally less demanding. Overlay in raster data sets include two or more different set of data that derive from a common grid. Each separate set of data are usually specified numerical values. In the raster, these values are mathematically merged together to create a new set of values for single output layer. The raster based overlay is done for create risk surfaces, sustainability assessment, value assessment and other procedures. For example, raster based overlay divide the habitat of an endangered species into a grade and then getting data for multiple factors that have an effect on the habitat, and then create a risk surface to illustrate what section of the habitat need protecting most. If two grids are aligned and have the same grid cell size, then it is relatively easily perform overlay operation. A new layer of value is produced from each pair of coincident cells. The values of these cells can be added, subtracted, divided or multiplied. The maximum value can be extracted, mean value calculated, a logical expression computed and so on. The output cell simply takes on a value equal to the result of the calculation. The raster data processing methods can be classified into different categories: local operation, neighborhood operation, regional operations. Local operation. Local operations are based on point by point or cell by cell analysis. The most important of this group is the overlay analysis. In the raster based analysis, either the logical or the arithmetic operators are used. The logical overlay methods use operators and, or, XOR, exclusive or, mathematically and multiplies the individual cell, whereas logical or exclusive or adds individual values of corresponding cells. The most important consideration in raster overlay is the appropriate coding of the features in the input layers. The raster overlay is affected by the resolution, that is the cell size, and the scale of measurement, that is nominal, ordinal, interval or ratio. It is advised that the resolution and the scale of measurement of both the input and the analysis layer should be compatible. Basic arithmetic operators in raster overlay operations are addition, subtraction, multiplication and division. Local neighborhood. Local neighborhood operations are also known as focal operations. It uses the topological relationship of adjacency between cells in the input raster layer to create a new layer. This operation assumes that the value of particular cell is affected by the value of the neighboring cell. Hence, a moving window of 3 × 3 cells is generally applied on the input raster layer. The value of the output cell may be either average of all the cells of the moving window or the central cell of the window or the median value of the window. Regional operations. Operators on region or regional operators are also known as zonal operation. Generally, a region is defined as the area with homogeneous characteristics. In raster model, it has been defined as the collection of cells that exhibit the same attribute characteristics. Though it also uses two input layer, but the mode of operation and the purpose is altogether different from the local operations, as it uses the boundary of one raster layer to extract the cell value from the other raster layer. The major purpose of this kind of operation is to obtain relevant data from an existing layer for further spatial analysis. There is no uncertainty in the location of the region boundaries because they are in perfect registration. Map algebra. Map algebra is a blanket term for comparing or analyzing the values contained within the cells of a raster layer, utilizing algebraic functions such as addition, subtraction, multiplication, division, statistical calculations such as mean, median and standard deviation, relationship operations such as greater than, lesser than, equal to, and Boolean operations such as not, and, or. By examining the mathematical solution of comparing two raster values, relationship between the two layers can be derived. One example of map algebra is the ability to find change in the landscape or change detection. Applying map algebra to the input and comparison of raster will expose the cells which change from bare land to forest. Types of overlay approaches. The three main overlay approaches available are weighted overlay, weighted sum, and the fuzzy overlay. Each approach has different basic premises and assumption. The most appropriate approach is depending on the overlay problem being solved. A summary of the approaches. Weighted overlay. In weighted overlay analysis, a series of tools can complement the weighted overlay tool to follow the general overlay analysis steps described. The weighted overlay tool scales the input data on the defined scale, the default being 1 to 9. The weights the input raster and adds them together. The more favorable location for each input criterion will be reclassified to the higher values such as 9. In the weighted overlay tool, the weights assigned to the input raster must equal 100%. The layers are multiplied by appropriate multiplier and for each cell values. The resulting value are added together. Weighted overlay assumes that more favorable factors results in the higher value in the output raster. Therefore, identifying these locations as being the best. Weighted sum. Weighted sum overlay analysis follows the same general steps of the overlay analysis described. Using the weighted sum tool complemented by other spatial analysis tool, and additive overlay analysis can be implemented. The values for the input layers need to be reclassified prior to using the weighted sum tool. Unlike the weights in the weighted overlay tool, the weights assigned to the input rasters can be any value and do not need to add to a specific sum. When adding the input raster, the weighted sum tool output values are direct result of addition of the multiplication of each value by the weights. Unlike weighted overlay, the values are not rescaled back to a defined scale. Therefore, it maintains the attribute resolution of the values entered in the model. Weighted sum assumes that more favorable factors results in the higher values in the final output raster. Therefore, identifying these locations as being the best. Fuzzy overlay. The fuzzy overlay analysis is based on the set theory. Set theory is a mathematical discipline quantifying the membership relationship of the phenomena to specify sets. In fuzzy overlay, a set generally corresponds to a class. Fuzzy overlay loosely follows the general analysis steps, but differs in the meaning of the reclassified values and results from combining the multiple criteria. The first three steps are the same: define the problem, break it into submodels and determine the significant layers. Like weighted overlay and weighted sum, Fuzzy overlay analysis reclassify or transforms the data value to a common scale, but the transformed value defined the possibility of belonging to a specified set, such as the slope values being transformed into possibility of belonging to a favorable suitability set from 0 to 1, with 1 defining being a member of the set. In weighted overlay and weighted sum, the values are on a ratio scale of preference, with the higher values being more favorable, unlike possibilities of membership as they are in the fuzzy overlay. Since the transformed values represent possibility of membership to sets, in fuzzy overlay analysis, the input raster are not weighted. In the addition and combined steps of the general overlay analysis, fuzzy overlay differs from weighted overlay and weighted sum. The combination analysis steps in fuzzy overlay analysis quantifies each location possibility of belonging to specified set from various input rasters. Application of overlay operation. A suitability model can be used to find the best location to construct a new school, hospital, police station, industrial corridors, etc. Certain land uses are more conducive than others for building a new school. For example, forest and agriculture were more favorable than residential housing in this model. It was decided to locate the school on flat slopes near recreation sites and far from existing schools. For the site suitability overlay, keep in mind some of the points. Selection of criteria, reclassifying the data as per the criteria, overlay, that is Boolean or map algebra, extraction and representation of suitable site. For example, criteria for nuclear waste repository site should be an area of suitable geology. Site must not be easily be accessible. Site must be away from high population, and site must be outside an area of conservation. Summary. Overlay is a general method for analysis of co-occurring geographic phenomena. Traditional maps are, in a sense, a product of an overlay process, where separate information layers such as roads, houses, types of land have been put together on top of each other. In GIS, the overlay process has been developed into an analytical tool where various forms of descriptive, deductive and inductive analysis can be performed on the data layers. As a noun, the term overlay also often refers to the individual layers in such analysis. Important application of overlay analysis include change analysis, spatial data accuracy assessment and various forms of multi-criteria evaluation. Overlay analysis tools allow you to apply weights to several input and combine them into single output. The most common application for overlay tool is suitability modeling. There are several approaches for performing overlay analysis. Although the methods differ, they all follow the same general steps for solving a multi-criteria problem. Since each approach is based on different assumption, the meaning of the number and the analysis techniques are specific to the approach, which one to the select will depend on the problem you are addressing. Overlay analysis is a group of methodologies applied in optimal site selection or suitability modeling. It is a technique for applying a common scale of values to diverse and dissimilar inputs to create an integrated analysis. Suitability model identify the best or most preferred location for a specific phenomena.